Hey everybody, Dr. White here with section 2.3 on some mathematical expectations that are special and important. So we already know about just the regular old expectation of a random variable x. You know, mu, or expected value of x, is the sum over the sample space of possible values of x of the particular value you get, little x, times the chance of getting exactly that value, f of x, little PMF there, okay? But we also were able to take the expected value of functions of a random variable x, and so we're going to look at some special functions of the random variable. So let's, for any k bigger than or equal to 0, k is just an integer, 0, 1, 2, 3, 4, so on. Let's define the kth moment of x about the origin as the expected value of x to the k, okay? So by the definition, that would be the sum over the sample space of little x to the k times f of little x. The kth moment of x about mu, which is the mean of x, the expected value, is the expected value of x minus mu quantity to the k. Okay, that's a function of the random variable x, which is another random variable, and here we are getting this expected value. And so, it would be written out according to the definition of expected value like that. Okay, so if you've done some physics, or if you studied moments back in Calculus 2, you can see the significance of the names. I'm not going to stress on the names much in this course, I'll just tend to say the kth moments, but we'll see more about that in just a moment. No pun intended. So a very special moment about mu is the second moment about mu, the expected value of quantity x minus mu squared. That is called the variance of the random variable x. So it can be written for short like var of x or sigma squared. We'll see why sigma in a moment. Let's go ahead and do an example where we compute the variance of a random variable straight up from its definition like this. But first, let me get my cup of coffee. Well, I'm getting it going. I'll get it in a minute. Well, since the definition involves knowing the mean of the random variable to start, then if somebody presents you with the probability mass function for a discrete random variable, you're going to have to first grab the mean. And so you just plug and chug, possible value times chance of that value, sum over all the values. And this time that sum comes out to a 1. So on average, you'd expect 1 out of this random variable, which kind of makes sense when you look at the random variable, because you got equal 1/4 chance to be 1 less and 1 more than 1, and 50% chance to be 1. So you kind of expect 1 on the average, and that's what the expected value is. Now we're ready for the variance. So all we got to do there is plug and chug possible value of x minus mu squared times chance of that value for x. So 0 minus 1 squared times a fourth, plus 1 minus 1 squared times a half, 2 minus 1 squared times a fourth. And just for fun, I'll simplify this out. Turns out to be a half, okay? Now, a very important related quantity is the square root of the variance of a random variable. So we'll call that just the letter sigma, since we were calling the variance sigma squared. So that's where sigma comes from. It's like we're already thinking ahead to the standard deviation. In this case, the standard deviation of the random variable x would be the square root of a half, which is 1 over the square root of 2. We'll get into standard deviations a whole lot more later. I just want to kind of give you a little foreshadowing here. The mean and the standard deviation of a random variable often work really well together to give you a good idea of the chances for the random variable to be in a certain range. In fact, for a lot of random variables that we're going to study, There are a lot of them. The chance that the random variable lands within sigma units of the mean of the random variable, that is the chance that it comes out bigger than mu minus sigma but less than mu plus sigma, that chance tends to be around 0.68 or so. It's a pretty rough rule of thumb. For some random variables, it's quite accurate, and we'll learn more about which type as we go on. Variance is so important that we try to compute it any quick way we can. And there's a shortcut formula for variance. And after I get my coffee, I'll tell you about it. So the shortcut rides on the properties of expected value that we learned about in the last section. See, we start with the variance of x, and we just trot out what it is by definition. And then we say, hey, let's square out the x minus mu squared, FOIL it out. So we're looking at the expected value of, sums and minuses of random variables. And so by the properties of expected value, that's the expected values, that's the sum and the minuses of the expected values of the random variables. And then you got things in the middle here like constant 2 mu times random variable x. And so the expected value of that is the constant times the expected value of x. And then proceeding a little further, you see here there was an expected value of the constant random variable mu squared, sticking at the end, and that would just be mu squared. So you end up with expected value of x squared minus 2 mu squared throwing back on a mu squared. And so the whole thing is expected value of x squared minus the expected value of x squared. That is a super useful formula. We'll constantly appeal to it. Let's take a sample distribution to play around with a little bit more. This one is called the uniform distribution because it's equally likely to be any of its possible values. Its possible values are 1, 2, 3, up to m. So actually, there's infinitely many of these distributions depending on how far you go before you stop at your m. Okay, so say your sample space, is 1 through m. Okay, so the probability mass function is simply 1 over m, equal likelihood here, for all the x's in that sample space. So the mean's pretty darned easy to compute. It's just you sum over all the possible values, 1 to m, x times the chance of x, 1 over m. Now, the 1 over m is a constant, so it can factor out of that sum. And you're left with the sum, x goes from 1 to m of x. Now, you may remember, maybe learned it in calculus, that there is a cool formula for the sum of the first n whole numbers. On the left of the equal sign is 1 plus 2 plus 3 all the way up to plus n. And it turns out that sum smacks down into, very conveniently, n times n plus 1 over 2. So you may have met it in calculus. You can prove it kind of geometrically or with mathematical induction. We might talk about this further if you'd like to ask. By the way, you can also sum up the first n squares of the whole numbers. 1 squared plus 2 squared all the way to plus n squared. And that turns out to be n times n plus 1 times 2n plus 1 over 6. You might have met that in calculus too. Well, anyway, I'm going to apply it here. This sum here is m times m plus 1 over 2. So I've got 1 over m times it, so there's a little bit of simplification. And the mean of this uniform random variable is m plus 1 over 2. It makes total sense. Like say that m was 4, okay? So you're looking at 1, 2, 3, 4, okay? 4 plus 1 over 2, that's 5 over 2, 2.5. And when you think about it, 0, 1, 1, 2, 3, 4. 2.5 is right smack in the middle of those. Okay, how about the variance? Well, once you got the mean, it's not terribly awful. So we'll use the shortcut formula. So now we're adding up the sum I goes from 1 to m of I squared times 1 over m. Might should have said sum x goes from 1 to m, x squared times 1 over m, just to remind you of x, possible value. But the sum is the same. And I've got to subtract off the square of the mean. So when I apply my sum of squares formula, then I get some math that I got to do. But when I do it, I get m squared minus 1 over 12. I encourage you to take your pen and pencil and your pencil and paper and stop this recording and just see if you can simplify this down to this. You always want to stop the screencast whenever any kind of interesting complex math goes on and see if you can fill in the details yourself. And then have, if you can't, like get stuck somewhere, just have that noted down as a question you'd like to ask later on in class. Okay, so we got the expected value and variance of a couple of random variables. Another really important kind of expected value is the moment generated function, moment generating function, MGF for short. You'll see why we call it that in a moment once we define it. Here's the definition. Let x be a random variable with a probability mass function f of x on some sample space S. And let's let t be some real number, like 2.7185110, whatever. And let's consider the expected value of e to the tx. That is a function. E to the tx is a function of the random variable x. It's a different function for each value of t you pick, but it's a function of the random variable x. It's another random variable whose expected value you may therefore take. So that would be the sum over all the x's in S of e to the tx times f of x. Now, infinite series, as you know, might converge and they might not. So this infinite series might converge for some t and diverge for other values of t. But if there exists a real number h bigger than 0, so that that sum converges for all t's between minus h and h, so if it converges in an interval around 0, even a small one, some interval around 0, then this function, m of t, is expected value of e to the tx, is called the moment generating function for x. We don't say there is one unless the set where it's defined includes an interval containing 0. So why should we think about moment generating functions? There are two reasons. Reason one, there's kind of a theorem in advanced math, like you could learn it in graduate school if you wanted, that tells you that if two random variables have the same moment generating function, they actually have the same distribution, meaning they have the same probability mass function, the same cumulative distribution function. Chances for them would work exactly the same way. So what that really means in practice is if you can find the moment generating function for some random variable, then you could learn anything else that you ever wanted to about that random variable. Okay? That's one thing. And the other, and this is the reason why it's called the moment generating function, is that it generates moments. You can use the moment generating function to find all of the kth moments around the origin. You don't believe me? Let me show you. Let's start off with m of t. Okay? And first, actually, let me just think about, like, what would be m of 0? If I put in 0 for t here, I'd have an e to the 0 times x. That's e to the 0, that's a 1. So I'd be summing up over all x in the sample space, just f of x. I'd be adding up all the probability masses. I would have to get 1. Now, the 0th moment around the origin is the expected value of x to the 0. That's the expected value of 1. That's 1. So m of 0 actually just gives you the 0th moment of x around the origin. But there's more. Take the first derivative. I claim it's what you see there, shaded in. Why? Well, you got to take the derivative of the sum. And as long as the sum converges fast enough, then you can actually just do the sum of the derivatives. And math theory says that this infinite sum, if it is infinite, will converge very, very fast. So you can think of it as the sum of derivatives. And so you get in here and think about having to take the derivative of e to the tx times f of x. With respect to t, see, this is m of t as a function of this real number t. Your variable here, as far as taking derivatives is concerned, is the t. Now, that means, well, f of x is a constant, so you've got a constant times a function of t. And so the derivative is going to be that same constant times the derivative of that function of t. So let's head over to the side here and think about taking the derivative of e to the tx with respect to t. Okay? Not x, not x, not x, okay? T. Well, the derivative of e to the something, according to the chain rule, is e to that same thing times the derivative of that thing with respect to t. And the derivative of tx, well, that would be the derivative of t times a constant. And so that would just be the constant, which is the x here. So the derivative of e to the tx is e to the tx times x in this situation where t is the variable you're differentiating on. So here's the derivative of e to the tx times that constant that it was being multiplied by. So we're looking at that sum now. That's the derivative of the moment generating function. Now, plug in 0 for t. So we're looking at the first derivative at 0. So we have an e to the t times, we have an e to the, we have an x times e to the 0 times x. Well, e to the 0 times x would be e to the 0, and that's a 1. So all we would get out of this is x times 1, which is x. We still have our f of x here. And when we look at that, that's exactly the definition of the expected value of x, the expected value of x to the 1, if you like, the mean. So the first derivative of the moment generating function evaluated at 0 delivered the first moment of x about the origin. What about the second derivative? Well, looking at the first derivative, take the derivative with respect to t. You've got some constants like the x and the f of x multiplying on, and that e to the tx inside, its derivative is going to be e to the tx times x, just like before. So there's throwing on basically just another x into the summands. All right, next step, put in 0 for t. And again, the e to the 0 times x is going to be a 1. You're left with the sum x over x and s of x squared times f of x. By definition, that's the second moment of x around the origin. So guess what? That shortcut formula for variance could actually be written in terms of derivatives of the moment generating function at 0. Second derivative at 0 minus first derivative at 0 squared. Pretty neat. You could keep going like that, and the rth derivative of the moment generating function at 0 would be the rth moment of the random variable around the origin. But our biggest concern tends to be the first and the second moments gotten out of the moment generating function, because from that we can get the means and the variances of our random variables. So Let's think back a little bit to that random variable that we met in the last section, where you're tossing a coin, and the chance of getting heads on any toss is, say, p, where p is some number between 0 and 1. You're going to toss the coin until you get a head for the first time. And you're going to let x be the number of tosses needed until the first head, including that toss that resulted in a head. And we found the probability mass function for x. So it was q to the x minus 1 times p, where q is the chance of a tails. Q is 1 minus p. And that made sense because you're getting x minus 1 tails, and then you're getting your head for the total x tosses it took to get a head. There's a name for this kind of random variable. We call them geometric random variables. Maybe because the powers remind us of geometric series. So there's a geometric random variable for every number p between 0 and 1. So I'd like to get the moment generating function for this geometric random variable. So I'm looking for the expected value of e to the tx for any real number t. So I look at my sample space, and it's 1, 2, 3, and so on. So I got to sum x is 1 to infinity. And then I got to do e to the tx times the f of x, which is the q to the x minus 1 times p. See that? Now, that looks like a tough sum to figure out. It doesn't look like a geometric series or anything like that. But it's actually kind of close to a geometric series because of those powers of x that occur in both the factors e to the tx and in that q to the x minus 1. In fact, I kind of wish it was a q to the x instead of a q to the x minus 1. So I'm going to make it that. I'm going to write a q to the x there. But that means I got to divide by a q to make up for it. And the p over q that you see here is it doesn't change as the x changes. So I can just like factor it out of the sum sign. Okay. Now inside, I see this e to the tx, which I'm going to use property of exponentials on and write it as e to the t to the x. And then I'm going to use another property of exponentials. Okay. Something to the x times something else to the x is the product of those two things to the x. And so, woohoo, we have almost got ourselves a geometric series here. It would be perfectly a geometric series if we were starting x goes from 0 to infinity, And so, like, how can we fix that? There's a couple of ways to do it. Let me show you a way I haven't shown you before. Just write out the series that you do have. So when x is 1, you have e to the t times q, and then e to the t q squared. E to the t times q squared is when x is 2, and so on. And, you could think of it like that. You could use a different index. I'm calling it j. And you could think of your terms as e to the t times q times e to the t times q to the j. And that way you start off with j being 0, and you would get just that e to the tq. And when j is 1, you would get 2 of the e to the tq's, and so on. So that's changing indices like that is a way to get the almost geometric series into a geometric series. And then we can say that it has to sum up to this. The little constant factor on the outside divided by 1 minus the ratio factor. Now you might think, does this really converge? Because the ratio factor has to be like less than 1 in absolute value. So let's leave that. Let's think about that later. But if it does converge, then let's see, the q's will cancel out. And I could write it like this. Or I could go back and take that q and make it a 1 minus p if I wanted as well. So when does that infinite series converge? Well, we need the absolute value of that ratio to be less than 1. Now, the ratio is positive always because of e to the t being positive and q being 1 minus p, so it has to also be between 0 and 1. So the product is definitely positive. So that's just the same as saying that that has to be less than 1. It's equal to its own absolute value because it's positive. So e to the t would have to be less than 1 over q. So t would have to be less than the natural log of both sides. And the log of 1 over q is minus the log of q. Now, minus log of q is actually a positive number because q is between 0 and 1, and the log of something between 0 and 1 is a negative number. So minus it's really a positive number. So what we got is convergence as long as t is less than that positive number. So we definitely have convergence in an interval around 0. I can just pick any age that's minus log q or less, and I'll have a convergence in that interval. So we totally have a moment generating function here, and it's defined for all of these t's. Okay. So once you have the moment generating function, what's it good for? Well, what we know it's good for is finding the expected value and the variance. And you remember that in the last section, we worked really hard and were quite clever in doing some summations to find the expected value of this geometric random variable. But the moment generating function technique is going to obviate the need for all that cleverness. All we got to do is find m prime of 0. So let's find the derivative, m prime of t, to start with. Do y'all know this? You know this way of talking about the quotient rule in calculus? We're going to have to use the quotient rule here because this is m of t, and it's the quotient of two functions of t. Here's the way I think of the quotient rule. I think of my quotient as a numerator over a denominator, and I'll call the numerator high and the denominator ho because that rhymes with low. Okay, so high over ho. And when I take the derivative, well, the way the quotient rule works is it's supposed to be, the bottom function times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. But when you think it out with highs and ho's, that turns out to be ho times the derivative of high, ho d high, minus high times the derivative of ho, high d ho, over the square of the ho, ho ho, So ho d high minus high d ho over ho ho. That's how I always remembered the quotient rule when I was young. Of course, you also, really serious about your calculus, you want to go back and look at how the quotient rule was proved and carry that along in your mind too. That's fine. Okay, well anyway, let's apply this quotient rule. So looking at our function, here's our ho. All right, let's get our d high. Head up there, that's a constant times e to the t. Derivative is going to be that same constant times e to the t, because derivative of t is e to the t. And here's our high, and then our d ho. Well, here was the ho, and the derivative of 1 is nothing, and the derivative of minus q e to the t is minus q e to the t. And here's our ho ho. So we stare at it a little while, and if we multiply some things out, we're going to have a p e to the t times 1. And we're going to get a minus qp e to the t. But we're also getting a plus qp e to the t there that cancels it out. So we're only going to be left with that initial p e to the t on top. Now take the moment generating function at t equals 0. Well, e to the 0 is 1, and so you're left with p over 1 minus q squared. 1 minus q is p, so you're left with p over p squared, which is going to reduce to 1 over p. That's the same answer we got when we worked so hard, so cleverly in the last section. Moment-generating functions kind of add on some calculational drudgery, but at least you don't have to be clever all the time if you can't be. The other thing you can do is get the variance. And that would have been really, really hard, clever thinking if you didn't have moment-generating functions. But with them, all you got to do is take the second derivative, which is going to mean the quotient rule again. So you're going to have a big fight with some algebra to kind of simplify it down. It turns out to this, a bunch of stuff over 1 minus QE to the t cubed. But you put in 0, and it turns out to be this. And then you throw it into the quick formula for variance. And so you got this. And you say, well, the 1 minus q cubed is really just a p cubed. And so there's a p that'll cancel from the top and the bottom there. And you'll be left with a 1 plus q over p squared. And there was a 1 over p squared waiting to be subtracted. So you're left with a q over p squared, or 1 minus p over p squared, if you like. And that's the variance. So I should just say, you're going to meet geometric random variables a bunch. And so you're going to want to memorize important facts about them, like their mean and their variances, and maybe even their moment-generating functions. So you're going to start looking a lot and practicing a lot with a little table of important probability distributions that shows up in the very, very front of your book, like right inside the cover. I've got a little PDF of it here that I just scanned it in. And so, like, you're going to be wanting to pay attention to this for the geometric random variable. So it's probability mass function, the moment generating function, the mean, the variance. Okay, why don't we hit up another example. Suppose I told you the moment generating function of a random variable x was this: 2/5 e to the t plus 1/5 e to the 2t plus 2/5 e to the 3t. If I tell you the moment generating function, theoretically, you should be able to find out everything else about the random variable. Can you find, therefore, its probability mass function, its mean, and its variance? Well, I want you to take a look at this. That's the moment generating function, which is supposed to be the expected value of e to the tx. So it's supposed to be the sum over all possible values of x of e to the tx times f of x. Well, these little powers of, that involve the t, those are your e to the tx's. So apparently one of the possible values for x was 3, because we see an e to the 3t there. Another possible value was 2. And if I stare at that and squint the right way, I can think of it as e to the 1t. And so a third possible value was a 1. And the numbers to the side must be the f of x's. So, kaboom, I can just write down the probability mass function for this random variable. There it is. And then I can get the mean however I like. I could use the moment generating function technique, but I think probably the easiest thing is just to use the definition straight up on the probability mass function table that I'm looking at. And when I do that and I simplify, I got to call me out if I'm wrong on that. I'll leave the variance to you. I'm getting tired of that example. But really, stop the screencast, find the variance, practice. How about number 13? So this one I think I want to read out of the book. Let's see here. Yeah. For each question on a multiple choice test, There are 5 possible answers, of which exactly one is correct. And they don't say how many questions there are, but I guess there's a lot. Because it goes on and says, if a student selects answers at random, give the probability that the first question answered correctly is question 4. They must have geometric random variables on the brain, because the first question you answer correctly, that would be your first success in your sequence of trying out questions. We're looking at a geometric random variable here, and since there's 5 options on each question and you're totally guessing each time, your chance of success each time is 0.2. And they're just asking what's the chance that it took 4 tries to get your first success. So I guess it comes down to the probability of 3 failures times chance of success. So 0.8 cubed times 0.2, which I can't be bothered to simplify. Let's try number 15. This is also about geometric random variables. They don't say so, but look at this. Apples are packaged automatically in 3-pound bags. Suppose that 4% of the time the bag of apples weighs less than 3 pounds. Okay. So like package after package is coming out of some machine. And 4% of the time they don't manage to get 3 pounds of apples in the bag. If you select bags randomly and weigh them in order to discover one underweight bag of apples. Okay, so like I get a bunch of bags and I just keep on weighing the bags until I find a bag that's underweight. Find the probability that the number of bags that must be selected is at least 20. Yeah, okay. So, let X be the number of bags you got to weigh until you get your first underweight one. X is clearly geometric, and they said that 4% of the time they're underweight, so the P is 0.04. And when they asked, what's the chance that you have to go through at least 20 of them before you get your first underweight bag, they're asking for the probability that X is bigger than or equal to 20. So officially, that would be the sum, X goes from 20 to infinity, of the f of X, q to the X minus 1 times P, and that's an infinite series, which, we could totally do, but I am so lazy. Why don't I just think about it this way? X is bigger than or equal to 20 means that it took 20 or more times to get your first underweight one. So the first 19 had to be not underweight. They had to be failures. And if the first 19 are failures, then it's definitely going to take you at least 20 tries to get your first underweight one. And so X bigger than or equal to 20 is the same event as the first 19 were not underweight. So all we got to do is find the probability the first 19 are okay, and that would be q to the 19th, 0.96 to the 19th. That's much easier than summing the geometric series. This might be a useful thing to keep in mind about geometric random variables. The probability that they're bigger than or equal to something is pretty simple. Part B says, what's the chance that you have to select at most 20? So again, doing it straightforwardly, you'd have to add up 20 f of x's. And that's not an infinite series, but still, it's too much work for me. So I'm going to think of probability of x being less than or equal to 20. That's 1 minus the probability that x is not less than or equal to 20, in which case x would have to be bigger than or equal to 21. And then using the same reasoning as before, I get 1 minus 0.96 to the 20th. Laziness in math is good. Look for these opportunities to use facts and theorems to shorten your work. Don't always go back to the definition every time. The last question they had was, what's the chance that it takes exactly 20 tries to get your first underweight one? And that's pretty straightforward. So that's special mathematical expectations. Out of this, you especially want to keep in mind the second moment about the mean. That's the variance. The square root of the variance, the standard deviation, is just a really great way, we'll see this as we go on, a really great way of saying about how much a random variable typically might differ from its expected value. And of course, you want to remember the moment generating function because it just seems to be awfully useful. Well, that's all for now. Let's see if I can find how to get out of here. There we go. See you later.